Guys, my name is Winstanley, and this is the intro to 2D kinematics, and thankfully we're sponsored by the FDA, and they're the ones who are making this video possible, so thanks FDA, saving your lives and giving you physics help. So 2D kinematics is basically the description of motion in 2 dimensions, which is the vertical and horizontal motion, and it's disregarding how the motion began. So in this episode, we're going to begin explaining some basics of 2D kinematics, and we're also going to give you some real-world examples and calculations to go along with them to help you in your physics class. Thank you.
Oh, I didn't see you there. One thing that's necessary before we continue on into 2D kinematics is the understanding of trig functions, which can be easily memorized by the phrase so, ka, toa, which stands for sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse, and tan equals opposite over adjacent. You can find the adjacent, opposite, or hypotenuse sides of the triangle based on this diagram, where the opposite is of course opposite from theta, the adjacent is adjacent to it, and the hypotenuse is always the longest length. If you're looking for the angle measurement of theta, you do a inverse sine, as can be seen here, where you take the inverse sine of opposite over hypotenuse, which gives you, in this case, theta. An example of how to find the length of one side of the triangle with an angle measurement can be seen here.
So Professor, Pythagorean theorem is a squared plus b squared equals c squared. This diagram shows a, b, and c. If a equals 3, b equals 4, a squared plus b squared equals c squared, which is 5.
One of the most important parts of 2D kinematics are horizontally launched projectiles. In this, we have an example where the initial, which sphere A and sphere B, are being launched at the exact same horizontal level parallel to the surface of the ground. In this, there's no vertical angle on either one of these, and B will be dropped directly straight down, and A will be launched with an initial horizontal velocity of 3 meters per second. And now, with this, we can also see that v of y initial is 0 because there's no angle on both of them. There's no acceleration in the x direction in either one of them, and the acceleration in the y direction will be the same of negative 9.8 meters per second squared on both. As you can see, in the end, the sphere B will go straight down, and sphere A will go to the left a little bit because it has a horizontal velocity. But as you can see, they will both land at t equals 6 seconds and t equals 6 seconds. For the initial, for the acceleration in the y direction is the exact same, and horizontal and vertical motion are completely separated. And this is assuming air resistance is negligible.
Oh, I didn't see you there. In the following example, you'll see why horizontal velocity stays constant regardless of vertical motion. Check out the example.
Watching the little demonstration, we can analyze it a little bit and compare it to some of the data we've seen before and apply it to some terms and conditions that we need to learn in general for horizontally launched projectiles and 2D kinematics. So this is just a generic graph of the ball. This is the y, so vertical. This is the distance, so horizontal, and we can see that it's increasing, its x direction is keeping going forward, and it goes up, reaches the maximum height, and then comes back down into David's hand. Now something very interesting, and the main point we're trying to get across here, is this is a velocity graph for the horizontal velocity compared to time, and this is the graph of the car, and this is the graph of the ball. Now, you can tell that the graphs are the exact same, and that is because when the ball is released from David's hand, it is actually going the same speed that the car is going, and since the car is not accelerating, the car and the ball will remain the same speed. And that's really the thing we're trying to get at right here, is that acceleration in the x direction for horizontally launched projectiles, or just any projectile, don't accelerate, and that is the main point we're trying to get across. So we can see this here, and it's also present here, as we can see that the acceleration in the x direction is 0. So even though these two things are completely different experiments, they still show the same concepts that are widely present throughout physics and 2D kinematics. A word from our sponsor.
Juling is not cool.
And to summarize, in 2D kinematics is the description of motion without regarding the beginning or the way the motion has began. In this, there's two different dimensions, the vertical and the horizontal motion. They're completely separate when calculating, and in this you can calculate 2D kinematics motion.